Okay, so let's do one more example just to for me to illustrate how important it is to check all the required conditions in order for us to have a meaningful model. Okay, that would be multiple linear regression. Okay, in the data files on Scholar, I've posted the file called real estate, and in the previous class at the end we discussed that houses can be priced according to many different predictors, right? So a lot of factors can affect the housing price. So let's download this file, and as we always do, move that file to the folder C data, right? Drive C folder data, okay? I believe I have it already there. Let me just check. C data, and the file is called real estate. So I'm not going to move anything. Where is my real estate? Yeah, real estate. Okay. So then start your RStudio, okay? And let's take a look at the file. Oh, I didn't. Laptop HDMI. I didn't realize that I'm not displaying anything on the screen. Oh, the laptop is not plugged in. All right. Okay, there you go. All right. So let me make it bigger. Okay, did you download the file? Real estate? Good. So let's investigate the file and let's see if we can build a decent model that allows us to predict the price of the house based on characteristics of the house, right? So I'm going to go ahead and read the file in real estate. That's how I'm going to call it. And that would be read.csv, right? And the file is located on drive C, folder data, and it's called real_estate.csv. Alright, so the file should give you no issues. Let's take a look at the structure, just like what it makes sense to do, right? Is that required? Well, no, but you want to take a look at what you're dealing with, okay? Let's take a look at the structure of the data real estate. Then, just like that. Okay? Alright, so what do we have? Well, apparently, in the data set we have 100 different houses, right? And there are 4 variables, 4 columns, that means. So, column number 1, price. That's our target, right? We want to be able to predict the price of the house. And the rest of them are predictors, okay? Number of bedrooms. I believe in the previous class we discussed that number of bedrooms can be important, right? Then house size, obviously. It would be weird if we didn't have this one. That's square footage, right? And also lot size, that's how big of a plot of land we have on which the house is built, okay? So, fairly simple model, 3 predictors, obviously 1 target. Okay, so let's go ahead and do the house pricing model. Okay, and of course I'm going to use the function LM, linear model, right? And my target is price. Everything else I'm going to use as my bunch of predictors, and the only thing that I need to specify is what data to use, and that would be real estate data. Okay? This one. So when I run this line, runs OK, and after that I have to say, show me the summary of my house pricing model. Okay? So let's take a look at the summary. Summary is right here. Okay. Well, first of all, number of bedrooms. Did you get the output, everybody? Got the output? Number of bedrooms. According to my model, as the number of bedrooms goes up, the price of the house goes up or down? up, right? So how do I interpret that number right there? It's for every extra bedroom, the price is expected to rise $4,306, provided that house didn't change, the size, right, didn't change, and the lot size didn't change, okay? So that makes sense. It goes up. How do I interpret that number right here? Well, it says that for each extra square foot of the house, the price is expected to go up by $74.30, right? Which, by the way, gives me kind of a nice example, kind of segue into the, I don't want it to become a big discussion, but how real estate is being appraised. This is one way to do it, okay? Build a regression model, and that slope, 74.29, that tells you that each square foot is worth, on average, $74.30, right? So this is one way how appraisers evaluate the house prices. They get the house to appraise. The house, let's say, has 2,500 square feet. They take the numbers from the regression equation, like this one, that's the price per square foot, multiply by the house size. That's your one way to estimate how much money this house is worth in the market. Okay? All right. Now lot size. Lot size, the way how I interpret that is every extra square foot of land that you're getting drives the price down by $4.36. Does that make sense? Now, more land, more expensive property, right? Obviously. This one says that more land drives the price down. That does make sense. That's my first red flag, that something is fishy with this model, okay? All right, so, but let's take a look at each of the variables individually, okay? How do we know if the variable is significant, contributing to the model or not? Well, we're looking at the p-value, right? What happens if p-value is large? By large, we mean more than, for example, 10%, 0.1, right? That means that, remember we test hypothesis now, the variable is significant, and flow other way around. Now this variable is not significant, right? Flow can be replaced with 0. An alternative variable is significant, flow has to stay the way it is. So, all of my three predictors have high p-values, right? So, according to what I have right here, bedrooms, number of bedrooms is not important, because it has high p-value. House size is not important, 0.16 the p-value. And lot size, out of all the variables, if anything, is the least significant variable, right? So my three predictors, all of them have high p-values, and therefore the model, it doesn't look like I have a model at all, right? I have three predictors, none of them are significant, and they should be. At least the house size should be important, right? It's obvious from general considerations and just makes sense from common sense standpoint, right? So why is this weird thing happening? Well, let's check the condition that we discussed in the last class, multi-collinearity. Remember which library did we use to check for multi-collinearity? GGLE. Which library did we use? GGLE, right? So go ahead and load the library. GGLE. It should still be installed on your machine. Okay. GGLE. Okay. And after that, I have to plot the matrix of scatter plots, really, right? I have to create a matrix of mutual scatter plots, pairwise. So I'm going to call the function ggpairs. And for the function ggpairs, I'm going to just apply the data set, right? That's my real estate. That's it. Okay? So when you run this line, it'll take some time. But at the end, over here, you will see beautiful plot. Okay? Just like this one. I'm going to make it slightly more compact. Okay. Alright. So, first of all, again, just like what we did in the previous class, right? I have columns and, yeah. So load the library GGLE and then call the function ggpairs, which comes from this library, and supply it with the data set, okay? And that's if you don't want to select any specific columns, right? So it plots all columns pretty much in one plot. Okay. So columns and rows in my graphical matrix, right? So price with bedroom, right? So here is my row price. Price is correlated with bedroom 0.645, with house size 0.748, and with lot size 0.741. So these are kind of strong correlations, right? With bedrooms, technical, I mean, according to our classification, it's moderately correlated, but it's on the brink of becoming strong, right? So I want these correlations to be weak or not so weak. They want to be strong. No, these ones I want to be strong, right? Because it's correlations with the target. Price is my target, right? I want my predictors to be strongly correlated with target. What I don't want is for them to be strongly correlated with each other. So, therefore, I ignore the first line completely. I can plot this matrix even without the price. I can exclude the price. That will be fine. So let's take a look at house size. How is it correlated with bedrooms? 0.846. Strong correlation, right? Does that make sense? It does, right? Bigger house, more bedroom. That's natural. So we expect this high correlation. Lot size with bedroom, 0.837. Also strong, which also makes sense, right? The bigger land you have, probably the bigger house you have, and therefore more bedrooms, right? And lot size with house size, almost perfect correlation, right? 0.99. And you can see actually right here is the scatter plot, right? You can see that this point, lot size and house size, they almost perfectly form the straight line, right? That's why your coefficient of correlation is so high, okay? So what I have is this. All of my predictors are strongly correlated with each other, right? So this is kind of an extreme bad case of multi-collinearity. And again, why do we not want two variables which are strongly correlated in the model? If they're strongly correlated, either positively or negatively, that means that if one changes, it makes big changes in another independent variable. Therefore, they're not independent anymore. But they kind of tell you the same story, okay? So for example, this one, lot size and house size, right? If a lot size gets bigger, house size almost proportionally gets bigger, always, according to our scatter plot, okay? So they're not really independent. They're hooked up, okay? And if you put them into the model as independent, that's what you're going to get. You're going to get weird things like this. Lot size has negative coefficient. It cannot, right? We know it cannot have negative coefficient, but it does. That is the result of the multi-collinearity. Then all of our variables, we know that all of them pretty much should be important, right, for the pricing of the house. But according to the p-values, none of them are important, okay? That again is the result of the multi-collinearity. So this is pretty much a good illustration why we should be looking out for multi-collinearity, for strong correlation between predictors. Because if you do have that, then this type of weirdness can happen, okay? And you have a model, but it's just awkward, right? So what's the solution? Eliminate things, okay? Just like what we did backwards. So let's try it, okay? So what's my most useless variable according to this? Lot size, right? Okay, so I'm going to eliminate lot size. Let's see. Minus lot size. And the summary. My summary says that house size is highly significant, right? I have 3 stars, but the bedroom is not, right? Plus, I know that bedrooms and house size, they're strongly correlated. So the next step for me would be to get rid of the bedrooms, right? Number of bedrooms, yeah. Yeah, that's what I'm doing. Yeah, no, I just eliminated lot size, and I have bedrooms and house size only in the model. The next one is bedroom, so I'm doing this stepwise backwards elimination. Bedrooms, and let's run the summary, and there it is, okay? So now I'm actually down to simple linear regression, right? And right now it says that each extra square foot in my house increases the value by $64.20, right? That's the only predictor. And kind of out of curiosity, let's compare the R squared. So my R squared for the model is 0.55. How about the models that I had before? 0.55, right? Same thing really. And my very original model, the very first one, 0.54, 0.56. So therefore, they're all about the same, right? So I started to eliminate variables which are strongly correlated. The accuracy of the model didn't really feel anything, right? It remained pretty much the same. So it basically means that these variables are extras, right? They're not useless, it's just they're duplicated, right? House size tells it all. High house implies big lot and big number of bedrooms. So therefore you don't need to include the rest of them, okay? So that's basically a good example to illustrate the importance of checking for multi-collinearity. Any questions, ladies and gentlemen? All right. Yeah, absolutely. The more useful predictors you can think of, the better it is, right? So therefore, data science, data analytics, what we're doing, right? We're doing scientific portion, okay? I'm showing you how to build a model, how to interpret them, how to evaluate if they're good or not so good, accuracy, misclassification rate, R squared, all that stuff. That's scientific portion, okay? Not so scientific portion is how do you pick the variables, right? What do you do? And that can be just plain accidental, okay? It can be like, all right, when was the last time house was renovated? Can we find that information? And sometimes it's a question of data availability as well. Because oftentimes, how can you get information on when they renovated the house? They only put the house on the market, they say, okay, we renovated last year. How do you check it? You can't, right? It's not public record. Yeah. So therefore, it's a question of, okay, even if we have that, how reliable is that, right? So a lot of considerations like that come into the play when building models. Okay, so it's only science to a certain degree. All right, so now, ladies and gentlemen, today we're going to start a new topic, which is called, and I'm going to post slides actually online, which is called logistic regression. Okay, logistic regression. Logistic regression. Okay. Now, let me ask you this question. So far, we learned more or less 3 models, right? 3 data analytics predictive models. The very first one that we did was classification tree. Is that a supervised or unsupervised model? Classification tree. Supervised, there is a target, right? And it's classification, right? Because the target is categorical, okay? And then we turned our attention to regression models. When target is numerical. Remember, we looked at regression tree. Right? We used the same example with Toyota Corolla. Okay, we created the tree structure where you can follow the branches, right, and arrive to the final node, and the node will tell you what's the price of this vehicle, right? So that was also supervised, and the target was numerical. Then we just finished multiple linear regression. Also supervised, right? And the target is numerical. Toyota Corolla, right? We'll use that example. Now we're going to turn our attention back to the classification. So logistic regression is a supervised machine learning, I'm going to abbreviate, machine learning method, okay? Method. And the target in this case, target is categorical. So specifically, we're going to turn our attention to case when the target is 0, 1. 0 for no and 1 for yes. Okay, in fact, we're going to use the example that we did before. Remember the bank, unsolicited loan offer. Bank sends out the letters or postcards to bank's customers and say, hey, do you want to take out a loan with a low interest rate, right? And it's unsolicited. Some customers say yes. Most of them say no, and then we basically find out why those people who agreed, what was so special about them, right? And we use that to build our classification tree, right? So in the next couple of weeks, we're going to take a look at how to build the logistic regression. Here is the weird part about logistic regression. by doing that. Okay. It is using the regression. That's why the word regression is in the name of this method. To predict 0-1 categorical outcome. It's really weird. Okay, so you will see exactly how it's done. All right, so let's kind of start slow. Okay, remember weeks and weeks ago we looked at the example. Oh God, what was that? Lawn mowers. People who buy lawn mowers, and we knew two things. It was really small data set. We knew two things about them: how much money they make, their income level, and also how much land they have. Because it's nature, right? The more land you have, the more grass you have to cut. Therefore, you probably need a lawnmower. Okay. So therefore, what I can expect is this: the bigger the land plot any person has, the more likely they are to buy the lawnmower. Sure. Bigger plot of land translates into the higher likelihood of buying a lawnmower. So here is one way how I can do it. I can get a data set, right? Hopefully, and let's say I'm simplistic. Okay, I'm saying that lot size. So lot size, alright, is one of my variables, and ownership is another one. Okay, so the first guy, for example, does not have a lawnmower, so he's a 0. Okay, and because I don't know, 0.7 acres. Okay, another one is a 0, he has 0.3. Okay, another one is a 1, he has 1.2. And there is another one, he has 3 acres. A lot of them. Okay, and there is a 0, 1.5. Okay, he's lazy, he hires somebody else to cut his grass. Okay, and then there is a 1 with 1.8, or something like this. Okay. Now, technically speaking, zeros and ones are numbers, right? I understand that they stand for yes and no, but let me be stupid for this one, okay? I'm going to say, these are numbers. Zeros and ones are numbers, last time I checked. And the lot sizes are also numbers. Can I fit a straight line into this bunch of points? I think I can. So my data set really will look like this. So lot size is my predictor, right? Lot size is the predictor. And here I have ownership, right? And the answers are either zeros or ones. So first person has 0.3, and he is right here, right? And this is 1. Okay. Next person is 0.7, so he is right here. He doesn't own a lawnmower, right? Then there was a 1.5. He is somewhere around here. Okay. Oh, but he is actually an owner, right? 1.5. No. Sorry. 1.5 is also a non-owner. So 1.5 is non-owner. And then I have 1.2, which is an owner right here. And then 1.8, which is right here. And then a 3, which is somewhere here, right? So this is just a bunch of points that I have. Okay? Again, I'm being ignorant about zeros and ones. I'm saying, that's not yes, no, 0, 1, okay? Let me treat them as numbers. Can I fit a straight line into this beautiful plot? Yeah, sure. R doesn't care, or Excel, or whatever else I use. It says, is your response a number? 0, 1. Yeah. Is your predictor a number? Both sides. Yeah. Okay, I'll fit whatever you want. So it will fit the straight line, and it will look like this probably, right? And after that, what I can do is, here's an idea. What is our standard cutoff for the classification? 0.5. Remember this? When we discussed the classification tree, we said anything above 0.5, proportion of yeses. If it's above 0.5, then we classify it as a yes. If proportion of yeses is below 0.5, proportion of no is above 0.5, and we classify it as a no. I'm going to do exactly the same thing, right? I'm being just ignorant about stuff. So I'm going to put my 0.5 right here, and after that I'm going to say, all right, if I take, for example, a person, let's say this is 1 acre, 1.0, okay, acres, then I'm going to predict that their proportion, their probability of being an owner is, oh, how much is it? I don't know, 0.4. So I classify them as what? Non-owner, right? They're below 0.5. This is my probability of, oh my God. Hold on. Yeah. this is the graph of my probability of F1, right? Probability of being an owner, okay? So if my probability of being an owner is 0.4, I'm going to classify that person as a no, right? On the other hand, here is somebody, right, with 2.0 acres. And I can do the same thing, then, and I estimate that their probability of being an owner is 0.8. Then I would classify that person as a yes, right? Beautiful. What's the problem? Well, the problem is, how do I deal with these numbers right here, okay? Somebody has 0.1, for example, and I will calculate their probability is minus 0.4. What's the minus 0.4 probability? This is crazy, right? There is no such thing, okay? At the same time, there is somebody right here with 2.5 acres, okay? And if I calculate their probability, it's going to be about 1. It's 1.2, something like this, okay? How do I interpret that? Probability is 1.2. More than a certainty? Crazy, right? So therefore, this ain't gonna work, okay? As much as I wanted to, it's not gonna work. But here is what I think might be a solution, okay? Now, you tell me if this is true or not. What my linear regression does is it takes all possible values of lot size right here in front of me, okay? Lot size can be anywhere from 0 to gigantic, plus infinity, right? And essentially, it creates a mapping of my lot size onto the vertical axis, which also can be like from 0 to plus infinity, right? All I have to do really is to say, well, I don't want my answers for the probability to be an owner to exceed 1, so I don't want the answer to be in this area, and I don't want the answers to be in the negative area, right? Right here, in the negative area. As long as my answer jumps between 0 and 1, that's what I'm looking for, okay? I don't want to cross out above 1, and I don't want to cross below 0, right? So my answer should be between 0 and 1. That's essentially the idea, okay? So, ladies and gentlemen, let's see how much you remember of pre-calculus. Okay? Alright, how should I start this? How many of you remember the function, let's see, y equals e to the power x? How do we call this function? Is it exponentiation? Exponential function, right? So, and what's e, by the way? Let's start with this one. What is e? Yeah, is it a number? It is a rational number, right? Do we know it? Pi is also a rational number, right? Pi is 3.1415 something, right? E is not related to pi. The only relation is that they're both irrational. Yes, I agree. Okay. Anybody remembers the value of e, the base for the exponential function? 2.7281, if I remember correctly, and then there's a lot of different numbers, right? And they don't repeat itself. That's one of the properties of rational numbers. They don't repeat itself. Funny fact, by the way. If you ask mathematicians, not related to data analytics at all, the funny fact. If you encode letters with numbers, right? For example, A is 1, B is 2, C is 3, okay? And if you get like a combination of numbers, right, you can convert them into letters, essentially, right? So if you get like infinite sequence of digits, numbers, you can convert the sequence into the letters, and therefore you can get like a string of characters, right? Well, the property of rational numbers is that they do not have a period, right? That means that what's a period? Period is like a sequence of digits. It can be a very long sequence, but it repeats itself, right? That's what rational numbers do, okay? They repeat. They have a period which repeats itself, right? Rational numbers don't have such a period. In other words, you can take any sequence, and it will never repeat itself. Okay, so it will will always be new. Okay. So the fun fact is, let's say, what's the famous book? Tell me, any famous book? Da Vinci Code. Okay, beautiful. Da Vinci Code. So if we encode numbers, if we encode characters, letters of alphabet with numbers, then you can take pi or e, right, and therefore convert the sequence of digits in each of these numbers, it's an instant sequence, into letters, A, B, C, etc., right? And because of the fact that you will see any and every combination of digits, somewhere inside E or inside pi, you will see the full text of Da Vinci Code or any other book, okay? War and Peace or Bible or whatever, okay? Kind of fun fact. All right, anyhow, let's go back to our task at hand with intent, right? Okay, so ladies and gentlemen, anybody, do you remember the graph of the function y equals e to the power of plus x? This is x. Well, let's start with this one. If x equals to 0, e to the power of 0 is how much? 1. Any number to the power of 0 is 1, right? So, therefore, we know that the graph should come to this point, 1, right? Well, if x goes to plus infinity, if I'm going to the right, then the function will grow very quickly. Exponential growth, you probably heard about. You heard this combination, right, of words, exponential growth. And at the same time, if x goes to minus infinity, it really quickly decays, but it never becomes 0. It comes really close to 0, but never becomes a 0. Okay? All right. So, well, let's draw another one. Okay. So, now I'm going to draw a function which is close but different. E to the power minus x. Okay? And horizontally I have x. So essentially what happens is negative x's become positive, positive become negative, right? It's as if I'm flipping the whole thing vertically around the vertical axis, right? So it still will go to the point 1 right here when x equals to 0, but now it will grow exponentially on the other end, so over here, okay? It will grow exponentially. Yeah, that's not very good. Okay, like this. And it will decay exponentially on the other end, okay? Now, ladies and gentlemen, why am I telling you this? Here, okay? Let me introduce you, ladies and gentlemen, a function which is called logistic function. Logistic function. Or sometimes it's also called logic. Okay? Just for the sake of briefness. Okay? The function looks like this. Y equals 1 divided by 1 plus e to the power minus x. Okay? This is going to be the basis for our logistic regression. By the way, it's not logistics regression, okay? I was making this mistake myself not so long ago, okay? Logistics is transportation, right, and distribution, okay? So this function has nothing to do with distribution of things in the supply chain sense of the word, okay? So let's draw this function, okay? So I'm going to have, horizontal and vertical axis right here, and this is x equals to 0. Okay, well, first things first. If x equals to 0, how much is e to the power minus 0? It's the same as e to the power plus 0, I'm guessing. And that would be what? 1, right? So therefore, y equals 1 divided by 1 plus 1, which is what? 0.5, right? 0.5. Okay, cool. So this is my 1, and this is 0.5, right here, 0.5. So I know that my logistic function will go to this one, okay? How are we doing so far? Yay? Cooper? It's going all right. Okay, that's a code word for I'm a little bit lost, but continue. Okay, so let's see if we can make more sense out of it. what happens if my x goes to plus infinity? In other words, I'm moving to the positive direction of the horizontal axis. Okay, well, let me go back to the function e to the power minus x. If x goes to plus infinity, then e to the power minus x goes to what number? This is how it goes, right? X goes to plus infinity. E to the power of minus x becomes closer and closer to what? To 0, right? E to the power minus x becomes closer and closer to 0, right? Practically glides over the horizontal axis. Okay? Alright, fine. So, I'm going to scroll down. So, if x goes to plus infinity, then e to the power minus x goes to 0, and therefore my logistic function, 1 divided by 1 plus e to the power minus x, so this term goes to 0, right? Therefore y goes to what? That becomes very, very small, right? This portion becomes very, very small, almost non-existent. It goes to 1, right? It goes to 1. Okay? So that means that this is how it looks on my chart, right? From point 5, as I'm getting to the higher and higher values of x, I'm getting closer and closer and closer to 1, right? But again, I never reach 1, okay? I can get very close to 1, but never actually touch 1, okay? Alright, well, let me go back to this graph. What happens if x goes to minus infinity? Goes to minus infinity. E to the power minus x goes where? To plus infinity, right? It becomes very high, right? So e to the power minus x goes to plus infinity, right? The function grows really quickly. So therefore, I'm going to write down again, if x goes to minus infinity, then e to the power minus x, it becomes minus minus infinity, right? Therefore, e to the power plus infinity, it becomes infinitely large, right? It goes to plus infinity. And then in this case, what y does? Y equals to 1 divided by 1 plus e to the power minus x. If this becomes really large, it goes to plus infinity. Then what happens to the function? Approaches 0, right? We're dividing 1 by huge number, right? So it approaches 0, okay? So therefore, my function, this is a graph of my logistic function, right? Logistic function. Okay? This is the graph of my logistic function. So therefore, as I'm getting to, as I'm getting to lower and lower values of x, I'm getting, man, I can't draw today. I'm getting to the values which are closer and closer and closer to 0. So this is how my function behaves. Okay? So do you see what happens? I take the whole range of my possible values of x, right? Ranging from minus infinity all the way to plus infinity, okay? And for each value of x, I'm getting the answers which are all squeezed into the range from 0 to 1, right? That's what my function does, right? I can plug in any number x to this function, logistic function, and the answer will be between 0 and 1, right? That's because the graph is squeezed between 0 and 1. Simple like that, okay? By the way, another name for the logistic function is sigmoid function, okay? Sigmoid function, okay? That's because its graph looks like a stylized kind of letter S, right? With really long tail, okay? Sigmoid. Alright. So why am I telling you all this, right? You can ask me, what, is it calculus 2? What are we doing here, right? Okay, here's the idea, okay? The reason why we're discussing that is logistic function is used to classify, to model the categorical target variable classified as 0, 1, yes or no, but it's using the regression behind it. And here is how, okay? In order to calculate the probability, here is literally what logistic regression looks like, okay? In order to calculate the probability of the answer being 1, for example, 1 being owner of the loan mover versus 0 non-owner, or 1 being somebody who accepted an offer, unsolicited offer of a loan from the bank, versus 0 somebody who didn't accept a loan from the bank. Or Titanic example, right? 1 if you survived, 0 if you died, okay? So probability of being a 1 is modeled as the following expression. 1 divided by 1 plus e to the power minus, but here now instead of x, here's what I'm going to do. I'm going to say same exact expression as we had for the linear regression. That means that m1 x1 plus slope times the variable, right? m2 times x2 plus dot dot dot. How many predictors can I have? As many as I want. The last one, for example, let's say I have k predictors, right? So I have mk times xk plus, last but not the least, the vertical y-intercept, okay? So I'm replacing the x in the function with this monster expression, okay? Which essentially, this portion looks like linear regression, does it not? We had this before, right? Variable times the slope plus another variable times the slope plus the intercept. That looks like linear regression, right? This portion, linear regression. But then what we do is we feed linear regression into the logistic function, and the answer, outcome out of that will be probability of being a 1, which will be between 0, well, I guess there is no equal, just plain less than 1 or greater than 0, okay? So the final answer out of this expression is going to be a value between 0 and 1. And that's exactly how we're going to classify things, okay? So first we find the values of m1, m2, mk, and the slope, and then you take any let's say, for example, right? Let's be specific in this case, okay? Let's say I want to build a model to predict which customer will agree to a loan. In fact, that's what we're going to do exactly. And which customer will not agree to the loan. X1, for example, is income. Okay, X2 is experience, years of experience. XK is, let's say, their average credit card balance, T3 balance, okay? Then about each customer in the bank, I know pretty much all of these things, right? I know their age, experience, income, credit card balance, everything, right? Then I plug the expression into this gigantic monster of a formula, right? All the values into this gigantic monster of a formula, and it spits an answer for me, which is between 0 and 1. And what do I do next, if you have to guess? At the end of the day, I have to say, this guy will agree to the loan, and this guy will not agree to the loan. How do I decide? Just have to... It's the same thing as we did with classification here, which is what? Exactly, cutoff value, standard, let's call it default cutoff value is 0.5. So, if my probability of 1 given by this expression will be above 0.5, I'm going to classify that as a 1. But if it's below 0.5, that's a 0. Okay? So this is the roadmap essentially for what is going to happen next week and then week after that. Okay? We're out of time, so on Monday, bring in your formula sheet, handwritten, R only multiple regression, right? Okay.